Alright, so in this video we're going to be discussing electrical power. One of our standards is analyzing electrical power used by an electronic device. This is where we're going to start, okay? One of the challenges that we're going to have right now is that we're doing this a little bit out of sequence. Generally we would have talked about energy first, but most of you have some chemistry experience, and so I just want to talk a little bit. We measure energy in joules, okay? And power is essentially the rate at which energy is being produced or used or created. And so power is just joules per time or joules per second. So 1 joule per second is defined as a watt. Okay? And another way that we can get a watt is if we multiply a volt times an amp. That's also equal to a watt. So what that means is amps are units for current, volts are units for voltage, and so V times I is equal to power. So we can say power equals voltage times current. Okay, now this is really significant, and this will allow us to kind of talk about why a light bulb lights up. It will allow us to talk about why a short circuit is bad and how kind of power consumption works. Okay, but the first thing we'll do is we'll just get some practice with this. So let's say that you have like a power brick for one of your devices, and you can actually go ahead and check if you look at like the plug for your computer, or more like a laptop, or whenever you have like one of those bricks that you plug in to convert AC to DC for your devices, it will have its power rating, and that's the maximum power it can produce. And so I have a charger for that has multiple USB ports, and it's rated for 50 watts, okay? And that's the power that it can produce. And since it's charging through USB, well, USB is 5 volts, okay? So if we have 5 volts and we have a capacity of 50 watts, then how much current do you think we could produce? Well, we could say 50 watts of power is equal to 5 volts times our current. And so what this means is, if we divide that over, 50 divided by 5 is 10 amps. Okay, and that's a lot of current. So if you're charging a phone at its maximum capacity, that's about 2 amps. So you could charge 5 phones really quickly with this, or you could charge like 10 phones slowly with this, is basically what the capacity of that charger is. Okay, so there's an example. The other day I was looking to purchase a power adapter for a different purpose. This one was also 5 volts, okay, and I was looking for the ability to produce a current of, actually let's do this one. There's a different one I was going to buy that I actually did buy, and I needed a 12 volt power supply that could produce basically 30 amps of current. Okay, so what power did this power supply need to be rated at in order to produce that amount of current? Well, if we multiply 12 volts times 30 amps, we get 360 watts. Okay, and so hopefully that you're starting to get the hang of this. It's a pretty simple calculation, and now we're gonna take a step back and talk a little bit about energy. Let's take a look at this circuit again. We have current going through this bulb. There's a voltage drop across this bulb, which means that power is being consumed by this bulb. There's energy being created or transformed by this bulb, and we see this power as the form of this radiation of this light. Okay, we can see this light coming out of the bulb. Okay, and if you look at what's happening on a molecular level, this light, there's a filament inside the light that's getting so hot that it starts to glow in visible light. And we'll talk a little bit about that more later in the semester. Okay? But whenever we have a current in a circuit, it's got to be creating some kind of power somewhere And if it's not creating light, then probably it's creating heat or sound. Those are the kind of the main ways we see energy being created. So if I put this here, there's nothing for it to do except create heat. And you'll see that when I minimize the resistance, we're getting a really high current. Okay? And so what's happening there is this. If we go back to our power equation, so our power equation says that P is equal to V times I, right? And we also know that with Ohm's law that V over R is equal to I. Okay? So if we put V over R in for I here, we get P is equal to V times V over R, or V squared over R. Okay? So power can also be calculated by multiplying V squared divided by resistance. Okay? So if you have a short circuit in a battery, you have some voltage and you have very little resistance. So resistance is really close to zero. It's not zero because everything has some resistance, but it's really close to zero. So if this value is really, really small, and this value is getting squared, so it's kind of getting amplified, then we produce a lot of power. Okay? And that power turns into heat. So whenever you have a battery or voltage source connected directly to itself, it's going to short out, it's going to produce a lot of current, and it's going to produce a lot of heat. And that's why, because it's creating power in the form of heat. Okay? And so that's why short circuits are bad and they could set fires, is because that energy turns into heat. And that's essentially what's going on there. And if you had an infrared camera, you could actually see this happening, not just with short circuits, but any kind of circuits. Those little plugs that you use for your cell phone to charge your cell phones, they're constantly have current flowing through them whether you're using or not, and they get warm. And so that's energy that's being wasted when these are plugged in and not being used. And if you had an infrared camera, you could see that this is warmer than everything else around it because of all that heat that's being produced. Okay? The last two things I want to show you are how we could use this in a circuit. So we'll look at a parallel and a series circuit before we wrap up. So let's say we have in this circuit a 9-volt power supply. Let's say we have a 3 ohm bulb and a 6 ohm bulb in series. Okay? And so what we want to do here is determine the power consumed by each bulb. Well, first we have to find the current using Ohm's law. V over R equals I. Well, the total resistance here would be 9. So 9 over 9 gives us 1 amp. So then if we're finding power, voltage times current, 3 volts times 1 amp gives us 3 watts here. And we'll do the same thing to get 6 watts of power here. So energy is being used at a rate of 3 joules per second here, 6 joules per second there. The combined energy consumption for the circuit, 9 volts times 1 amp, is 9 watts, or 3 plus 6 is 9. Okay, and so that's one way we can look at power within a circuit. Also in a parallel circuit, let's say that we have a 10 ohm bulb and a 3 ohm bulb connected, okay, and we have a voltage of 9 volts here. And so if we want to find the power of this circuit, we first have to find the current through each bulb. And so how much current, well, I'll do this first one. So current through this bulb here would be 9 over 10, or 0.9 amps. Okay, what would be the current through this 3 ohm bulb right here? 9 over 3, 3 amps. So put that right here. So this is going to be 3 amps. How much total current through the circuit? Well, that would be 3 plus 0.9, or 3.9 amps. Okay, so if we want to find power, 9 volts times 3.9 amps, that's going to give us about 36, just under 36, about 35.1. watts of total power for this one right here. So across each of these we have a 9-volt drop. Okay, so for this one right here, that's going to be 3 amps times 9 volts, or 27 watts of power consumed by this bulb. We have 0.9 amps going through this one with a 9-volt drop, so that's going to be 8.1 watts of power consumed by this bulb. Okay, and that's basically it. That's using power. That's really all the different ways we're going to see it. I encourage you to look at power adapters, because not only will you see a rating for power in watts, you might also see a rating for current, most likely in milliamps. Okay, they'll have both of those, and what those mean is the maximum it's capable of producing. Okay?